Hi, so in this video I'm going to show you an example where I'll use that three-step method for approaching calculation questions to work out what's going on with quite a complicated looking calculation, and then we'll see how it helps us get a better idea about what's going on and be a little bit more confident with the question. Okay. Now, I still use this method myself. After all these years of doing calculation questions like this, I still always rely on this because I think it just makes it so much easier to make sense of what's happening. And if you really know what's going on, you are more likely to actually get the correct answer. And when I ask my students what they've learned that they've found most helpful, quite often they say that this method is the thing that has made the biggest difference. So I really think it's worth adopting this method and using it when you answer calculation questions. Now, we went through the full steps involved in this and the full details of this in the lesson notes, so I'm not going to talk you through absolutely everything again here, but we'll just quickly run through what we're doing. So the first step is to get organised. That involves doing various things, such as working out the full balanced equation so we can see the stoichiometry, just organising all of the information around the equation so we can see what we've got, and thinking about how many significant figures you need for your final answer. Second step, we need to work out what our final step in the calculation needs to be, because even if we don't know what we've got going on with the rest of the calculation, if we can at least figure out what we need to do to get that final answer, we've got something to work towards and it all starts becoming a little bit clearer. And then we need to just find two usable pieces of information to start with. So you don't need to worry at this stage about whether you actually know how to do absolutely everything you need to do to get to that final step. You just need to find something that will let you get started. Because often, once you've done one thing, it jogs your memory about what to do next. And then you'll go from there and you'll eventually get somewhere. Or, even if you're totally lost, as long as you can get two pieces of information to start with, you can most likely get the first mark, and that's better than nothing if it comes to it. Yeah. So the question that we've got to work with is a not very nice one, but these are exactly the kind of questions that you want to apply this method to. So let's see what we've got. So we're told we've got a 5.2 gram sample of impure sodium carbonate. It was dissolved in water and made up to 250 centimetres cubed. 25 centimetres cubed of this solution required 26.40 centimetres cubed of 0.2500 molar hydrochloric acid for neutralisation. Calculate the percentage purity of the sodium carbonate. So I can see that I've got a reaction involved here, and that means I need a full balanced equation so that I can see the stoichiometry. Now, this is a reaction between a carbonate and an acid, and we had a lesson where we talked about working out the reactions of acids earlier. So if you haven't already been through that lesson, it would be a good idea to go back and have a look at that as soon as you can. But for now, I'm going to assume that you have done that lesson, so you've got an idea about what's happening. So the equation is sodium carbonate plus HCl. And since this is a carbonate reacting with an acid, we'll get a salt, which will be sodium chloride. We'll get water and carbon dioxide. Now it's not balanced, so I need to balance it before we go any further. And I'll use the method that we went through earlier for balancing equations as well. So 2 sodiums on the left, 1 on the right, so 2 goes there. 1 carbon, that's fine. Ignore the oxygens, ignore the hydrogens. I've got 1 chlorine on the left, 2 on the right, so 2 goes there. Okay, so everything is balanced up now, and now that I've got my equation, I can see that I've got a 1:2 ratio. Now, if I didn't take time to do the equation and work that out, I might end up just assuming it's a 1:1 ratio and making a mistake there, which is not what we want to be doing. Okay, so let's go through the equation now and have a look at the information we've been given, and I'll write down everything I know about each of these reactants underneath it. Now, I'll just change my pen colour, bear with me. Okay, so I've got 5.2 grams of impure sodium carbonate, so 5.25 grams there. That was dissolved in water and made up to 250 centimetres cubed. This 250 centimetres cubed then belongs to the sodium carbonate. And 25.0 centimetres cubed of this solution. Now, this is where the confusion often comes in. We've got a second volume, and a lot of students go a little bit on autopilot here and just put the second volume with the second reactant. But for these longer questions, it's really important to think about what they're actually doing from a practical point of view. So what are they doing with these volumes? Well, let's go back and have a look. So we took the impure sodium carbonate and we dissolved it in water and made it up to 250 centimetres cubed. And then it says 25 centimetres cubed of this solution, so this solution is 25 centimetres cubed out of that 250. So they've made up a larger volume of sodium carbonate solution, but they're only using a small portion of that, only 25 centimetres cubed in that next step. Now we'll talk about what to do with these volumes later, but for now I'm just going to put the 25.0 centimetres cubed of sodium carbonate down here because that second volume also belongs to the sodium carbonate. Okay. Now, continuing with the rest of the information, so 25 centimetres cubed of this solution required 26.40 centimetres cubed of the 0.250 molar hydrochloric acid. So these two pieces of information here belong to the hydrochloric acid, so that's 26.40 centimetres cubed, 0.250 capital M. Now that capital M stands for molarity. It means moles per decimetre cubed. A lot of students end up thinking that the capital M means moles and end up tripping over because of that, but it doesn't. Capital M means moles per decimetre cubed, okay? If you see the units MOL, that means moles, okay? But this capital M seems to be creeping into the exam questions a little bit more lately, so watch out for that and don't let that confuse you, okay? Right, I'm nice and organised now. I can see what I've got to work with, so the next thing for me to do before I go any further is work out how many significant figures I need for the final answer. Now it's important to do this because you don't want to end up rounding too early, so if you work out how many significant figures you need for the final answer, you know to keep more significant figures than that in at each stage. So if we have a look at what we've got, remember the significant figures for your final answer is determined by the lowest number of significant figures in the data. So all of our data here is given to 3 significant figures, apart from this 26.40 here, so that's 4 significant figures. But given that the lowest number of significant figures in the data is 3, we want to have 3 significant figures for the final answer. So I'm just going to put a reminder. I want 3 significant figures there. Now that means at any intermediate steps, I want to be rounding to at least 4 significant figures, a minimum of 4 significant figures. If you're in doubt, keep more significant figures in, okay? Now that doesn't mean I'm just going to stick extra zeros on the end of it to give me 4 significant figures. You know, if I do a calculation and the answer comes out as a nice round number with just 2 significant figures, say, that's fine, yeah? But if you've got a big long string of digits on your calculator, you need to round to 4 significant figures and keep those in until you get to the final step, okay? So I'm nice and organised. I know I want 3 significant figures for the final answer, and I can figure out what my final step needs to be now. So I've been asked to calculate the percentage purity of the sodium carbonate. Now the percentage purity is calculated like this. I'll just write this at the top. So percentage purity is equal to the pure mass divided by the total mass times 100. Now, at this stage, I should have one of those pieces of information already, okay? So I need to go back and see what I've got. Remember, the percentage purity we're interested in is for the sodium carbonate. So if we see what we've got for the sodium carbonate, we have a mass there. We have that 5.25 grams. Now, we can use that 5.25 grams as our total mass, okay? And I'm just going to put that 5.25 grams in the expression there, and I'll cross out the 5.25 grams underneath the sodium carbonate so that I know that I've already figured out where I'm using that and I don't accidentally use it elsewhere, okay? Now just examining this equation a little bit. The percentage purity, pure mass divided by the total mass there. To get the pure mass, this is what we'll be able to get by working out the number of moles of sodium carbonate. If we know the number of moles of sodium carbonate in that sample, then we can do moles times the relative formula mass, and that will give us the pure mass. So that's the aim for this calculation now. We want to get the moles of sodium carbonate so we can work out that pure mass, okay? Now I'm just going to leave that there as a reminder about that's what I'm aiming for, because if you ever get lost along the way, have a look at what your final step needs to be and you can check in and see how close you are, okay? Now we're almost ready to get going, so let's have a look at what data we've got left to use and decide what our two usable pieces of information are. Now we want the moles of sodium carbonate, but if you have a look at what we've got for sodium carbonate at the minute, there's not really anything we can do with that. We've got two random volumes there. That's not going to get us anywhere. So we need to leave the sodium carbonate a little bit and see what we know about the HCl. So for the HCl, we've got the concentration and volume there. So we can work out the number of moles of HCl. And once we've got the moles of HCl, we'll be able to get the moles of sodium carbonate and we'll be on our way to getting the answer. Okay? So our two usable pieces of information will be these two, and we'll use those to calculate the moles. Okay? Now, I'm going to show you how to do this calculation in the next video. But before I do, you might want to pause this and have a go at this calculation yourself, because you should by now have a good idea about what's going on. You should be able to work out what you've got. And even if you can't go right through and get the final answer, so for example, if you don't really know what's going on with these volumes, you can do something. So have a go, and I'll see you in the next video.